Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 28. In this lecture, we'll discuss the geometric optics of lenses. This topic is covered in Chapter 36 of our textbook by Surway and Jowett. In this lecture, we want to discuss the optics of lenses. It turns out the optics of lenses is really determined by the law of refraction. So in principle, if you understand Snell's law, then you understand everything you need to know about how lenses work. The problem is that you need to systematically apply Snell's law to many rays before you can understand how and where a lens creates an image. So in this lecture, we want to simplify that process. To begin with, I want to present you with a simple, crude model of a lens. Specifically, I want to talk about a converging lens. Turns out that all lenses fall into two categories, converging lenses and diverging lenses. We'll start with converging lenses on this slide, and then on the next slide, we'll discuss diverging lenses. To begin with, consider a triangular prism. So this is basically a triangular piece of glass. We've discussed the optics of prisms before. Now we want to discuss what happens when a single beam of light is incident on this prism. Hopefully by now you understand that when a beam of light is incident on the prism, it's going to bend. It's going to refract once at the left surface and then once again on the right surface. There may be other things that happen as well, for example, dispersion. However, for now, we're really only interested in refraction. So we're going to assume that the light is monochromatic or that it consists of a single frequency. Specifically, what we want to consider is this horizontal beam of light. This beam of light is horizontal, or more precisely, it's parallel to the base of the triangle, and when it strikes the prism on the left side, it refracts by some amount. It travels through the prism, and then when it strikes the second or the right side of the prism, it again bends or refracts and then eventually emerges from the prism. Now consider another prism. This second prism is identical to the first one, but it's been flipped upside down. If you understood what happens to the first prism, then you should understand what happens to the second prism. In general, the incoming beam is going to bend towards the base of the prism. So for the lower prism, again, a horizontal beam comes in, it's incident on the prism, it's going to refract twice and eventually bend towards the base of the prism. As you can see, these two rays of light that were initially horizontal and parallel to each other are now seen to cross or intersect each other at a single point. Let's consider a third piece of glass. This third piece of glass is simply a rectangular block of glass. Again, we want to know what happens when a horizontal beam comes in. This horizontal beam strikes the left side of this block. The angle of incidence is 0, so the angle of refraction will be 0, according to Snell's law. And then again, it will strike the second or the right side of that block, and the angle of incidence is 0, so the angle of refraction is 0. Basically, this beam passes right through the rectangular prism without changing its direction. Now, if we were given the apex angle for this prism and we were given the index of refraction of the glass, we could calculate these angles precisely, but that's not what we're interested in right now. The important point right now is that the three beams that used to be parallel now seem to intersect each other. The three beams are converging or coming to a focus at a single point. Now you might be wondering what happens to other beams. Well, here are two other beams of light that are also horizontal, and these two new beams will also converge to a single point, although the point that they converge to is different than the point that other beams converge to. So what we have here is a contraption that is capable of taking parallel beams of light and then forcing them to come to a focus. This is a crude model of a lens. However, it's not a very good lens because, as you can see, different rays will focus at different points. Ideally, we would like to have a lens that makes all of these rays come to focus at a single point. If you think about this a little bit, you can see what the problem is. The problem is that the angle needs to change. So as we get closer to the center of the lens, we would like to have a surface that is a little more vertical. And as we go to the edges of the lens, we'd like to have a surface that's a little more horizontal. This can be achieved by polishing the glass. So in reality, the way lenses are made is that one starts with a rough cut piece of glass and then polishes, grinds and polishes that piece of glass to the perfect shape. That perfect shape ends up being something like this. This is the shape that we often associate with lenses. In this class, we'll be discussing spherical lenses, so the left surface and the right surface are arcs of a circle. So if you take the piece of glass, grind it down, and then polish it to a smooth spherical finish, what you'll get is exactly a lens. So you just saw a crude model for a converging lens. A converging lens is capable of bringing rays of light together. Now let's talk about a diverging lens. A diverging lens actually separates or fans out the rays of light. Here's a crude model for a diverging lens. Once again, we'll start with a prism, but now our first prism is already upside down. You know what happens when a horizontal beam of light strikes this prism. It bends towards the base of the prism. If there were an observer on the right side, if this beam of light were to end up in the eye of the observer would assume that this beam of light is coming somewhere along this line of sight, this extended ray. Now consider another prism flipped relative to the first prism. Again, consider a horizontal beam of light. As usual, that beam of light is going to bend towards the base of the prism. If this beam of light were to end up in the eye of an observer, the observer would extend that ray backwards and assume that this ray is coming somewhere from some point along this line of sight here. Now suppose that we modify the middle of this contraption and we simply install a rectangular piece of glass there. What happens to a horizontal beam of light that passes through this rectangular piece of glass? Well, nothing. It'll go straight through, and if this third beam were to end up in the eye of an observer, the observer would assume that the light is coming from some point along this line. So if these three beams of light were to end up in the eye of an observer, located somewhere on the right-hand side, the observer would assume that all three beams are emerging or emanating from this single point of intersection. Now you might be wondering what happens to other beams of light. Here are two more beams of light, and those two beams also seem to emanate from a single point, although it's a different point than the one we were considering earlier. So what we have here is a crude model for a diverging lens. As you can see, this contraption here takes beams of light that are initially parallel to each other and fans them out so that they are diverging from each other. And if these beams were to end up in the eyes of an observer, they would appear to be coming from these virtual focal points on the left side of the lens. Now, this is not a very good lens because we would like all of these to appear to be coming from a single point. Right now, it seems like we have multiple focal points. The solution, once again, is to take this rough cut piece of glass and grind it and then polish it into a nice smooth surface. The surface that we want to achieve is a spherical surface. So we have one arc of a circle on the left side and another arc of a circle on the right side. This shape here is the shape of a perfect diverging lens. The most important property of a lens is its focal length. As we've just seen, lenses have the ability to focus light. Converging lenses tend to focus the real rays, while diverging lenses tend to focus the virtual rays. In either case, the distance from the lens to the focal point is going to be very important for us. We'd like to be able to calculate that focal length. To calculate the focal length of a lens, we need to know something about the geometry of the lens. Each lens has two surfaces. There's the left side and there's the right side of the lens. These surfaces could have any shape in general. However, we will assume that the shapes are always spherical. So we will assume that each face of the lens is an arc of a circle, essentially. Since each face is essentially an arc of a circle, each face is associated with a radius. So to characterize the geometry of a lens, we'll start by specifying the radius of the left surface and the radius of the right surface. Lenses can be symmetric, but they don't have to, so in general, R1 can be different from R2. Also note that each face is associated with a center. In this particular picture, the left face of the lens is part of a circle that might look like this, and associated with that circle is this center here. And then the right side of the lens, which has radius R2, is also part of a circle, which I might draw like this, for example, and that circle also has a center here. If we want to understand the optics of a particular lens, we need to understand how these two radii affect the focal length of this particular lens. Before we calculate the focal length, we need to establish some conventions for how these radii are measured. In general, R1 and R2 are considered to be positive when the center is in the back of the lens, and R1 or R2 are assumed to be negative when the center is in the front. When I say front and back, what I mean is essentially where the light starts and where the light ends. In most of the diagrams that I'll be drawing for you, I will assume that the light is propagating from left to right. So I'm going to assume that the light comes in like this, and then perhaps it does something like this. So in this particular case, we would say that the left side is the front of the lens and the right side is the back of the lens. Although you should be careful, because in general, you can simply move the source of light to the other side and reverse this. In every example, you really need to think carefully about where the light starts and where the light ends up, and that initial and final position is what tells you where the front and the back is. In any case, what's important for us is to note that the R's can be positive or negative depending on where the center associated with that surface is. So these are just conventions that you basically should memorize. Now for ideal lenses, all of the horizontal beams will come to focus at a single point. We refer to that point as the focal point. Note that the focal point applies to these horizontal beams. And by horizontal, more precisely, I mean beams of light that are initially parallel to the optical axis. The optical axis is a straight line that passes through the center of the lens and is perpendicular to the lens at that point. What we now want to calculate is the distance from the lens to the focal point. The focal point of a lens is given to us by this formula here. This formula can also be written in this form here. The form on the right is a little more symmetric and probably easier to memorize, but the form on the left is actually how you calculate the focal length. In either case, you need to know what R1 is, and remember that R1 could be positive or negative depending on how the surface is curved. You also need to know what R2 is. You also need to know what N is. N is the index of refraction for the glass or whatever material you've made the lens from. The formula that I just presented to you for the focal length of a lens can be applied to both converging and diverging lenses. However, when the formula is applied to a converging lens, the resulting number is always a positive number. In fact, this is really how we define a converging lens. Given some arbitrary lens, you calculate its focal length, And if f happens to be a positive number, then you can be sure that you have a converging lens. You have a lens that brings the real rays of light to a focal point. We can also say that a converging lens converges parallel rays of light on the back side of the lens. Here are some examples of converging lenses. The biconvex lens is typically what we think of, but these other two lenses, the convex concave lens and the plano-convex lens, are also converging lenses. In other words, when parallel beams of light are incident on all three of these lenses, those beams come to a focus on the right side or the back side of the lens. Notice that in all these cases, the lens is basically thicker in the middle than it is on the edges. So in practice, in the laboratory, if you find a lens and you're wondering whether it's converging or diverging, you can usually feel the surface of the lens with your fingers, and comparing the thickness in the middle to the edges, you can tell whether this is a converging lens or not. A diverging lens, on the other hand, is one whose focal length is a negative number. So we're using the same formula. However, because the shapes are different, R1 and R2 are going to be different, and ultimately F will be different. If the focal length for a lens is a negative number, then we say we have a diverging lenses. Diverging lenses don't really focus the real rays, they focus the virtual rays. So we can say that the parallel rays of light that are incident on a diverging lens, they tend to diverge on the backside, and they just appear to be coming from a focal point on the front side of the lens. Here are some examples of diverging lenses. The biconvex lens is normally what we think of when we speak of a diverging lens, but diverging lenses can also come in other shapes, like the convex concave lens and the plano concave lens. Notice that in all three cases, the diverging lenses are thinner in the middle and thicker on the edges. That's the exact opposite pattern to converging lenses. So once again, if you come across a lens in a laboratory, you can feel the lens with your fingers, although you have to make sure you don't smudge the lens. And if the lens appears to be thinner in the middle than it is on the edges, then you know you have a diverging lens. So far, we've been discussing what happens when horizontal beams of light are incident on a lens. So we know that when horizontal beams of light, that is beams that are parallel to the optical axis, are incident on a lens, they come to a focus. For converging lenses, they come to focus on the right side or the back side of the lens, and for diverging lenses, they come to focus on the left side or the front side of the lens. However, that doesn't tell us how a lens actually creates an image. To understand how image is formed, we will start with ray tracing, like what we did with mirrors in our previous lecture. Before we attempt ray tracing, you should understand that each lens has two focal points. Each focal point is the same distance from the lens, so the distance from the lens to the right focal point is f, and the distance from the left focal point to the lens is also f. So to calculate the focal length, you need the formula that I presented to you earlier. But once you have that focal length, you need to understand that there is a focal point on the left and another one on the right. The reason for this is because in theory, light could come at the lens from either direction. So you could have light that is incident from left to right, in which case that light would come to a focus on the right side, but you could also have the opposite. In principle, you could shine light on the lens from the right side, and that light will come to a focus on the left focal point. So you need to indicate both focal points to begin with. Once you've done that, you can place an object in front and then trace individual rays that emanate from the object. As usual, we're going to assume that there are many rays of light that are emanating from the object in every direction, but of course it's a little difficult talking about all of them all at once, so we'll consider a few key rays of light. Here is an important one, a beam of light that is traveling horizontally, parallel to the optical axis. This one should be easy. A lens is basically designed to ensure that this type of array passes through the focal point. So we can say that this lens will make this particular ray pass through the focal point on the right side. Here's another important ray. This one already passes through the focal point on the left side. As you can probably guess, this one is going to bend, it's going to refract upwards, and it will bend enough so that it emerges from the lens traveling parallel to the optical axis. To see this better, you can ask yourself what would happen if this ray were actually coming from the right. Well, as it goes to the left of the lens, it would have to pass through the focal point. So if it's already passing through the focal point, then it will end up being parallel to the optical axis. There's a third one that we could talk about. This is the ray that is aimed at the very center of the lens. This particular ray happens to go through undeviated, so it goes straight through the center of the lens, a little bit like how a beam of light would pass right through a rectangular piece of glass. If these three beams of light were to end up in the eye of an observer, he would assume that they're coming from this point here. This point here is the only point that is common to all three paths of light, so we can say that an image forms at that point. More precisely, an image of the tip of the object forms here. You can repeat this process with other points along the length of the object, and you would see that those points also essentially get imaged to various points along this yellow arrow. So we would say that this converging lens creates an upside down image at this location. We would describe this image as a real image because, as you can see, it is formed at the intersection of real rays. Eventually, we'll have formulas that tell us precisely where this image forms, but for now, it's important that you understand ray tracing like this because the concept of how images are formed are not really conveyed by the equations. Diverging lenses are also capable of creating images. Let's repeat the same ray tracing process with a diverging lens. Once again, note that a diverging lens, like a converging lens, has two focal points. Each focal point is the same distance from the lens. That distance is known as the focal length of the lens, but you must place a focal point on the left and one on the right because in principle, light could be incident on the lens from either side. We now place an object in front of the lens. By convention, we'll place the object on the left side so that initially the light rays are traveling left to right. There are many rays that emanate from this object, but we want to systematically consider a few key rays, and this is one of them. This ray is parallel to the optical axis. By now you should know that this particular ray will bend upwards as it enters and then exits the lens. How much up will it go? Well, it will appear as if it is emanating from this point here. So the extension of this particular ray will appear to pass through the focal point on the left side. We could also consider a ray that is aimed directly at the focal point, but not the left focal point, but the right focal point. This particular ray will also bend upwards compared to its original direction of propagation. How much up will it bend? Well, enough to make it parallel to the optical axis. You can imagine that this ray is traveling in the opposite direction from right to left. In that case, you would see that as this ray comes in, it will bend upwards and it will appear to come from this focal point. So if it's initially already going towards that focal point, it will end up being parallel to the optical axis. We could consider a third ray. This ray is going for the center of the lens. The rays that that are incident on the center of the lens pass through undeviated, so it will pass straight through the center of the lens. And if these three rays were to end up in the eye of an observer standing somewhere on the right side, looking at the object through the lens, it would appear as if these three rays of light are emanating from this point here. As you can see, this point here is the only point in space that is common to all three rays. So we would say that an image forms over here. If an observer were looking at this object through this lens, he would see a right side up image that is actually smaller than the object. We would describe this image as a virtual image because it is formed not at the intersection of these real rays, but at the intersection of virtual rays. Recall that I'm using dashed lines for virtual rays. This dashed line here, for example, does not represent actual light waves. It is simply the line of sight. It's what the vision system assumes must be there by extending the real ray backwards. As you've seen, ray tracing provides a nice visual description of how and where an image is formed by a lens. Unfortunately, ray tracing does not provide the exact location or size of the image. For that, we need the thin lens formula. The thin lens formula, shown here, relates object distance, image distance, and the focal length of the lens. Notice that the thin lens formula is actually identical to the mirror formula that we saw in our previous lecture. The reason for that is that in this course, we're considering only spherical mirrors and spherical lenses. So the basic geometry of these objects is essentially similar. There are some differences in how you use the formulas. In particular, the conventions for P, Q, and F are a little bit different for lenses than they are from mirrors. P is the distance from the lens to the object, so the lens is the center of every measurement, it's the reference point. And P can be positive or negative. If the object is in front, then P is a positive number. If the object is in the back, then P is a negative number. At this point, it may not make sense why an object would be placed in the back of a lens. Later, when we discuss multi-element systems with multiple lenses and mirrors, this will make a little more sense. Q is the distance from the lens again, but this time to the image, and Q can be positive or negative. When the image is real, that is in the back of the lens, Q is positive. When the image is virtual, that is in front of the lens, it is negative. Typically, the thin lens formula is used to calculate the image distance in terms of P and F, the object distance and the focal length. So although the thin lens formula is normally written in this nice symmetric form on the left, in practice, you'll end up using this form on the right. The two equations are identical. If you start with the left equation and solve for Q, you'll simply get this equation on the right. However, it's worth your while to memorize both forms because in practice, you'll often be given the object distance and the focal length for a lens, and you'll be asked where is the image, and so you can calculate that using this formula on the right. To plug in numbers into this formula and obtain the correct image distance, you should be familiar with the conventions for the focal length. Remember that the focal length is simply the distance from the lens to the focal point. Each lens has two focal points. You can consider either one. That distance is the focal length. The focal length is a positive number for converging lenses, and it's a negative number for diverging lenses. The thin lens formula is quite important because it tells us where the image is located. Unfortunately, the thin lens formula does not provide any information about the size or orientation of the image. As you probably noticed when we were ray tracing, the image can be bigger or smaller than the object. And sometimes the image is upright, sometimes it is inverted. To know the orientation or the size of the image, we need to know the magnification of the lens. Magnification is defined as the height of the image divided by height of the object. So you can imagine a scenario as follows. You have a lens, could be of either kind, converging or diverging, and you have an object, and this lens will create an image of the object. This could be the lens of an eye, could be the lens of a camera or a telescope. The point is that the object has some height and its image will have some height as well. The ratio of these two heights is known as the magnification of the lens. It can be shown that the magnification is equal to minus q over p. So if we know the object distance and we know the image distance, then that ratio will give us the magnification of that particular lens. Of course, you can use the thin lens formula to solve for q and then substitute that into this formula, and then you will find that the magnification can also be expressed as minus the focal length divided by p minus f. The magnification provides information about the size and orientation of the image. For a positive magnification, the image is upright. For negative magnification, the image is inverted. If the magnification is between 0 and 1, the image is smaller, but if the magnification is between 1 and infinity, for example 12, then the image is going to be larger and it'll be 12 times bigger. If the magnification is minus 12, then the image is inverted, but it is 12 times bigger. The optics of spherical lenses is described by two important equations, the thin lens equation and the magnification equation, which I presented on the previous slide. You may have noticed that I did not derive either one of those equations. And the reason is that a detailed derivation of these formulas is usually not illuminating. That's not always the case in physics, but in optics, it turns out the conceptual understanding and application of the formulas is usually more important than the detailed derivation. The detailed derivation usually involves a whole lot of geometry and trigonometry and many approximations, and seeing a detailed derivation usually doesn't make you any better at actually using optics. That's why until now I've focused on the conceptual understanding and the practical applications of optics. Nonetheless, I think it's important for you to see at least an outline of the derivation. So for the next 3 slides, I'm going to present to you an outline of the derivation for some of these formulas. And later, if you are interested in a detailed derivation, you can at least use this outline to derive the results on your own time. The optics of spherical lenses essentially boils down to refraction. In particular, the optics is determined by how rays of light refract when they go from one medium to another. So in this picture, I have 2 media, for example, air and glass, although what's important is that one medium has index n1 and the other medium has index n2. A beam of light starts at point O, travels at some angle alpha, strikes the boundary between the 2 media at point P, it refracts or bends and ends up at point I. Eventually, you'll see that point O represents the object and point I represents the image. We will assume that the boundary or the surface that separates the 2 media is spherical in shape, and therefore it must have a center indicated by the letter C here. The radius of a circle, of course, is perpendicular to the tangent, so we can use the radius as the normal to this surface. The angle of incidence would be theta 1 and the angle of refraction would be theta 2. R, of course, denotes the radius of this circle. The basic setup is described by multiple parameters. Ultimately, what we want is an equation that relates n1 and n2, the 2 indices of refraction, and of course the object distance, the image distance, and the radius of this circular surface. In all, we have 12 parameters to consider, although we don't expect all of them to show up in our final equations. However, as you look at this picture here, you can see there is a lot that's going on. The 2 indices of refraction, object distance, image distance, the radius that describes the geometry of the surface, but of course also t, which is the distance from this point on the lens to point P, that's the horizontal distance. D is also going to play a role. D is the vertical distance from P to the optical axis. There's alpha and beta. Alpha describes the initial angle of propagation for the ray. There's also gamma, which is the final angle of propagation relative to the optical axis. And of course, theta 1 and theta 2, the angle of incidence and the angle of refraction. So we have 12 parameters, but we really only care about 5 of them. So we will use 7 equations to derive an equation involving only 5 parameters. In other words, we will use 7 equations to eliminate 7 of the 12 parameters, leaving us with the 5 that are often important in an optical application like this. So now I want to list 7 equations that are going to relate the 12 parameters you see on this picture. With the help of these 7 equations, we're going to reduce our 12 parameters to only 5 essential parameters. The first equation is really an approximation. T is approximately equal to 0. What I'm saying here is that this thickness here must be relatively small. In effect, we're saying that we want to consider only thin lenses, not thick lenses. It turns out most optical applications involve thin lenses. The second equation is from trigonometry. We're considering this angle here and the right triangle defined by this angle here. Tangent of alpha is the opposite leg, which is d, divided by the adjacent leg, which is this distance here, and that's equal to p plus t. Of course, we're assuming that t is approximately equal to 0, so we can discard t from the equation. We're also going to assume that alpha is a relatively small number. In this picture, it doesn't seem like alpha is a small angle, but of course, in reality, we want to really consider rays that are propagating at very shallow angles like this. I've exaggerated the angles here so you can see the geometry a little more clearly, but alpha really in actual practice is a small number, and therefore tangent of alpha can be approximated as alpha. To see that, you would have to perform a Taylor series expansion of tangent, and you would see that the first essential term in the power series expansion is just alpha. So the end result is that alpha is approximately equal to d over p. Our next equation is similar. Now we're focusing on this angle here, and we're looking at the right triangle defined by this corner. Tangent of beta is going to be the opposite leg, which is d, divided by the adjacent leg, which is r minus t. Once again, t is approximated as 0, and tangent of beta for small angles can be approximated as beta. Our next equation is similar. We're focusing now on a different angle, gamma over here, and the large right triangle defined by this corner here. Tangent of gamma is d, which is the opposite leg, divided by the adjacent leg, which is this distance here, and as you can see, that's q minus t. Once again, we're going to approximate t as 0, and we're going to approximate tangent of gamma as gamma. The next equation we have should look familiar to you. This is the law of refraction, or Snell's law. It relates the two indices of refraction and also the angles theta 1 and theta 2. It turns out if alpha is small, then theta 1 and theta 2 will also be small, which means that we can approximate sine of theta 1 as theta 1 and sine of theta 2 as theta 2. Therefore, for small angles, Snell's law reduces to this equation. N1 theta 1 is approximately equal to N2 theta 2. The next equation does not involve any approximations. It's an exact equation. If you look at the triangle that is defined by these 3 vertices, you'll see that the angle alpha plus the angle beta plus this angle here must equal to 180 degrees or pi radians. The angle here that we're interested in, of course, is pi minus theta 1. So equation 6 is simply saying that the sum of the angles of this triangle is equal to pi radians or 180 degrees. Equation 7 is derived similarly. We're now looking at a slightly different triangle. We're looking at the triangle defined by these three vertices. Angle gamma plus angle theta 2 plus this angle here, which is pi minus beta. They must all add up to pi radians or 180 degrees. So we now have 7 equations that relate a variety of parameters together. We can now use these 7 equations to eliminate at least 7 of the 12 parameters you see in this picture. So just to summarize, we're looking at the details of refraction as a single beam of light goes from one medium into another. We found that to describe the situation, we need 12 parameters or 12 variables. And on the previous slide, we came up with 7 equations that will help us eliminate some of those parameters. If you now take equations 1, 2, 3, and 4 from the previous slide and substitute them into equation 6 and then do some algebra to solve for theta 1, you'll arrive at this equation here. This is something that I'm sure you're capable of doing, although the algebra might take you some time. You can also take equations 1, 2, 3, 4, and 5 from the previous slide and plug them into equation 7 and again solve for theta 1, in which case you would come up with this new equation for theta 1. Both of these equations, of course, are for theta 1, so you could equate the two equations, and when you do that, you find this equation here after simplifying the algebra a bit. This equation here is referred to as the refracting surface formula. You can already see that this resembles the thin lens formula, although it's not exactly the same thing. It's not exactly the same thing because so far we've only considered a single ray as it goes from air to glass, for example. To complete the derivation, we would want to repeat these entire calculations one more time, but this time from glass back to air. The refracting surface formula is sometimes written in this form here, which is even more similar to the thin lens equation, and F in this context is defined as N2 over N2 minus N1 times the radius of the refracting surface. So we have not really done a detailed derivation of the thin lens formula, but here I'm just giving you an outline of how you could arrive at something that is quite similar to the thin lens formula. And if you go a few steps further, you can then transform this formula into exactly the thin lens formula. And that is the end of this lecture. Thank you for your attention.